Swayam Prabha. Digital India. Educated India.
Welcome to the third lecture of Module 6. From this lecture onwards, we will focus on the powder bed based additive manufacturing systems. And in today's lecture particularly, we shall discuss about the laser based powder bed additive manufacturing systems. So this is going to be the content of this lecture. We shall start first defining further the powder bed additive manufacturing, and then the typical architecture of a laser based powder bed additive manufacturing system. Then based on the subcomponents of the machine used particularly for powder bed additive manufacturing, we will classify the system, and then we shall discuss about its subcomponents. So as we have already seen, the powder additive manufacturing systems are classified into powder bed systems and powder feed additive manufacturing systems. We have already discussed about the powder feed additive manufacturing systems. Now our focus in this module will be on powder bed additive manufacturing systems. The powder bed additive manufacturing systems are usually classified into two categories. Either the particle of the powder which is spreaded on a bed are joined together by utilizing a binder deposited from the top, or these powder particles are joined together by giving a thermal energy to it through an energy beam. So further, this powder bed additive manufacturing is usually classified into two categories. One is the binder based powder bed additive manufacturing, and another is laser beam based powder bed additive manufacturing. So first we will discuss about the energy beam based powder bed additive manufacturing. Further, the energy beam could be of two types. We already know that. Either it can be a laser beam or it can be an electron beam. So this particular lecture will be on laser beam based powder bed additive manufacturing. So this is going to be the focus of this particular lecture. So a typical timeline for the history of powder bed based additive manufacturing is shown on this slide. Here you can see that the first powder bed based additive manufacturing system was basically invented in around 1971, where Professor P. Crowd given an application of powder laser process for making the objects. Then after that, in around 1984, Professor R. Householder gave a description of a process which is very similar to selective laser sintering. Then also around the similar time, Professor C. Hull provided detailed working method and apparatus for building the object layer by layer. Then later on in 1986 to 1987, Professor C. Descartes has developed the process called selective laser sintering. So he usually considered to be the father of the powder bed based additive manufacturing system. In the similar time, in around 1987 to 1988, Professor M. Feigen developed a machine for powder based process very similar to selective laser sintering. Development of these powder bed systems, particularly by Professor C. Descartes, gave birth to the corporation like DTM Corporation, and of course the 3D system was already there, which was commercially selling the systems for SLA. Later on, few more companies came into picture over the period of time, as shown here on the right side in the red color, and the left side black color thing is showing for the further development of the process. In around 1997 and 1998, Professor R. Larson has developed the process called electron beam melting. In this case, instead of laser, electron beam was used to melt the powder. Later on, after 2000, when high powered laser also came into picture based on diode and the fiber, a group which is shown here developed the process called selective laser melting. So, there is a difference. Before that, laser beam based powder bed additive manufacturing system was governed by the sintering operation, while this group brought a difference and replaced the sintering with melting. So, typically this is how a laser beam based powder bed additive manufacturing should look like. This is a schematic for the same. Here there is a powder material which you are seeing here, which is spreaded on a right side platform, and this platform is called as the build platform. The powder like material comes from a reservoir which is here in this schematic shown here on the left side. So, this is the reservoir, and powder is delivered by the upward motion of this plate on the left side. This plate goes up by the desired layer thickness, and the material is available, a layer of powder is available to get deposit on the right side where the build platform is going downward. This is typically called as a powder delivery system. There could be different means also of providing the appropriate amount of material to the recoater to spread this on the build platform. There are different powder delivery systems. Then also there is a recoater, which is nothing but a blade which takes away the right amount of powder and moves absolutely on a horizontal line and spread this collected powder into the cavity which is created by the motion of the build platform after completion of the part. When the new material or the new powder particles are spreaded over this build platform, then the next step starts. So, there could be different means also for recoating the layer. After spreading a new layer of powder onto the build platform, then usually a diode or fiber laser nowadays is used, which got reflected by a mirror which is mounted on a hinge and able to deflect the beam on the XY plane. We know this optics or the group of lenses here is called as nothing but the galvanometer. In general, we can call it as the laser scanning system. There could be different means of moving the laser spot on the bed in the XY plane. Then when the laser beam strikes and interact with the powder particles, the different mechanisms occur in order to join the powder particles together. It could be like sintering, it could be laser phase sintering, or it could be the melting of the powder itself on the bed. Based on the appropriate joining mechanism, the part is created. It may happen that the support may be required. However, it can be noted that the support may not be required in laser beam based powder bed additive manufacturing to prevent the downward motion of the overhanging feature, but it is required to prevent the upward motion of the layer. So, let us consider that we are scanning this thin layer of the powder and it is scanned by a laser beam. In that case, the powder got melted and formed a solid layer. And now during the cool down phase, and assume that it is a large overhang, meaning to say there is no solid part under this, but there are powder particles. So, while scanning this powder layer on the top, definitely it will be supported from the bottom by the loose powder particles. They will not allow this layer to fall down. So, that is not our worry here, but as it is a tiny layer of around 40 micron, and if it is a very large overhang, then it may happen that after solidification this layer may warp like this. this layer may warp like this, and it is due to the residual stresses into the layer. And if the layer got warped, we know that this recoater may hit it and there may be chances of not able to realize the or complete the part efficiently. Therefore, usually if the material used here is prone for the deflection, it is prevented by providing appropriate support so that it does not allow this layer to warp up and kept it straight while depositing the large overhangs. So, this is a typical architecture for any laser beam based powder bed additive manufacturing system, but it can be noted that the subsystems used in this particular machine can vary. However, there are different types of the subsystems, those serve the same purpose in different machines. Like for example, the laser beam which is striking on a optics and then getting deflected on the XY plane, which is called as the galvanometer, can be replaced by the flying optics, where the laser head itself can be mounted on two prismatic joints. Then the laser head itself can move in X and Y direction. The entire optics of the laser can now fly. Also, the powder material which we use here can be of different types. It can be plastic material, it can be powder coated with the polymer, or it can be the metal material, or it can be ceramic coated with some polymer, or it can be pure metal as well. So, that is why the subsystems can be of different variants, and let us now identify these subsystems. The first one is of course the powder material. Like I said, it could be ceramic, it could be polymer, it could be metal. The second is the joining mechanism. How these powder particles are going to join. Are they going to join by the sintering, or they are going to join by melting, or they are going to join by liquid phase sintering. Third possibility is how you are going to scan the spreaded layer on the XY plane, whether it is scanned by a galvanometric system, or it is scanned by the flying optics, or it is scanned by putting a mask under the floodlight. The fourth one is the powder delivery system. How you are delivering the right amount of powder which can be spreaded on the cavity created on the build platform. The fifth subsystem is how you are going to spread this layer onto the build platform, and that is called as the recoating system. Recoating system could be like it is a simple blade which is moving like here from left to right and spread the layer. Also, this blade itself could be of different types, like it can be a soft blade of silicone, or it can be a brush like material, or it can be like a brush, or it could be a ceramic blade, or it could be a metal blade. Also, in some cases, instead of a recoater having just only a blade, there could be a counter rotating roller as well, which not only spread the layer but compact the layer which we are spreading. So, these are the different options available for powder recoating system. The sixth subsystem is the build atmosphere, meaning to say the entire process is happening in an open environment, meaning to say there is no inert environment in it, or it is happening in an inert environment where the entire atmosphere is having only one single type of gas like argon or nitrogen. Or it could be possible nowadays that in some system the entire system is kept under vacuum and there are no air molecules inside it. So, these are the possibilities for build atmosphere. And the seventh subsystem is of course the build platform on which you are building the part. So, we will discuss in detail about the different types of these subsystems, and then we shall discuss by appropriately collecting the combination of these subsystems, and then we shall discuss about the appropriate combinations of these subsystems in the commercially available machines. So, let us now discuss each and every subsystem of the laser beam based powder bed additive manufacturing. The first is of course the joining mechanism. How two layers are going to join together in the case of laser beam based powder bed additive manufacturing. So, the first very common method is the sintering. In the case of sintering, one applies enough heat to further bond the particles, but the heat should not be enough to reach the melting point of the particles. Typically, the temperature is between the half of the melting temperature to the melting temperature, because in this temperature range only various physical and chemical reaction occur, and the most important, which is the diffusion, which used to occur in this particular range of temperature for most of the materials. Now, what happened in diffusion? It involves basically the neck formation between the adjacent two particles. The main driving force for sintering is the lowering of the free energy when particles grow together. So, if for example these are the two particles close together and the temperature is increased, then in that case this neck which is formed between these two particles keep on growing and its radius keeps on reducing over the period of time. Of course, they will definitely not completely get merged because the temperature is always below the melting temperature. However, a gradient in the vacancy concentration between the highly curved neck, which is in the beginning, it's having a very high curve as you can see, becomes flat later on, which is usually for the low vacancy concentration, and it causes the flux of vacancies from neck and a flux of atoms towards the neck, thus increase the neck size till it becomes almost flat. So, this is a typical mechanism for solid state sintering. The foremost advantage of the solid state sintering is its capability of its adaptability with any material. A wide range of materials can be processed with sintering, starting from polymer to metal and even the metals and ceramics coated with some polymers. The another mechanism for joining the two layers in the powder bed additive manufacturing is something called as liquid phase sintering. So, liquid phase sintering is a sintering technique that uses a liquid phase to accelerate the interparticle bonding of the solid phase. In this case, of course, high diffusion rates are associated with liquids, giving fast sintering or lower sintering temperatures. It involves sintering under the condition where solid grains coexist with the wetting liquid. So, two possible types of liquid phase sintering are with the two types of particles. First is with mixed powders, where the liquid is formed by the lowest melting point component, and the second is the pre-alloyed powder, where supersolidus liquid phase sintering governs the process. So, let me just consider now again a case of liquid phase sintering where there are particles greater in size and small in size. This is typically the bigger size particles are called as the structure particles, while these small particles are called as the binders. These binders are usually of a low melting point temperature material, and these bigger size particle or structure particles are of high melting point temperature. When a laser beam moves over it, these low melting point particles get melted and they make a matrix around in the system in which these structure particles are sintered. So, the final product can be as it is, or in some cases it is considered as a green state part and later on it is kept into the furnace to do further processing of the part. Next is the another layer joining mechanism is by the melting. The melting applies sufficient heat and increase the temperature of powder particle above the melting point. And as the temperature is now above the melting point, it causes the particles to completely melt. And when the particle melts, they form a bridge between the adjacent melted particle, and hence the entire zone got solidified, and we usually produce 100% dense part by this process if it is successful. Now let us talk about the different types of powder particle possible in laser beam based powder bed additive manufacturing. The first one is the coated particles, the second is the mixed particles, the third is pre-alloyed particles. Fourth is either pure polymer or wax or pure metals. To process these particles, usually two routes of sintering taken place. First is called as indirect route and the second is called as the direct route. In the case of indirect route, the laser beam does not melt or sinter the powder particles of the desirable material, while a sacrificial binding material is used, which usually melts away and makes the bond with the adjacent materials. In that case, preferably the coated particle and mixed particles are preferred. Of course, the part produced by the indirect route will always require some post processing, because on the powder bed, by utilizing the indirect route, we will always produce some green parts. They will taken out from the bed. Yes, of course, the part produced in the bed should have sufficient strength that one can take it out without destroying it, and then they should go to some station where the further sintering can happen. To do that, of course, we have to increase the temperature of the component produced by this method, and the binder should burn off. And then later on, the porosities left behind due to the evaporation or burn of these binders, these porosities are usually filled by some infiltrate material. So, as the process happened in two stages and directly we are not producing the main object on the powder bed, this type of process are called as indirect route or indirect selective laser sintering. Like I already mentioned, typically either the coated particle or mixed particles are used in the case of indirect route. The another possibility is the direct route. In the case of direct route, the laser beam melts or sinter the powder particles of the desirable material on the powder bed itself, and usually no post processing or minimal post processing is required, but complete sintering usually happen in the powder bed itself. So, the direct routes are applicable for mixed powder, for pre-alloyed powder, for polymers and for metals as well. So, now let us discuss in detail about these indirect routes and direct routes, because that will give us further details inside the need of this type of powder particles to be used in indirect route or in direct route. So, let us first discuss about the powder material for indirect route. Like I have already mentioned, the coated particles are the most preferable powder particles for indirect route. The coating can be of any material that exhibits a lower viscosity upon heating. The thermoplastics satisfy this requirement. They also can be repeatedly heated to soften or melt and cool down to solidify as the temperature passes through the glass saturation temperature to the melting temperature of the thermoplastic. So, for example, when a ceramic or metal parts are desired, the powder particles of these materials are coated with some thermoplastics, and these thermoelastic polymers act as a fugitive binders. So, the idea is basically to have a low melting point material adjacent to the powder substrate, so that the latter is more easily compacted to produce the green parts. So, for example, if this is my ceramic particle and assume that these particles are coated with another material which is having a melting temperature lower than the red color particle or the main particle. Now, when a laser beam will move over these powder particles, the green color material which is having a low melting point will get melted, and it will easily form the bond between the adjacent material, and that too with the green color. As a result, in the entire system, if you see, there will be a matrix basically of these low melting point temperature in the solidified part, and these center parts, those are of high melting point, will be compacted together into this matrix. This particular part which we produce by melting the low melting point temperature in the bed, this particular part is called as the green part. As I already mentioned, it used to have the sufficient strength that one can take it out, remove the area where the loose powder is available, that acts as a support here, and take it out and keep it in furnace to do the further processing. Then later on, the binders available in the green part are either chemically converted to a higher melting point substance or thermally decomposed and eliminated. Like I mentioned, there are two possibilities now. Either we just eliminate these binders from the green part, and or we supply appropriate chemical in such a way that after reaction with the chemical provided, the melting point of these binders can increase. However, the later one, which is the thermal decomposition, is most popular. So, like I said, the binder elimination route is more preferable, and if it is taken in the first stage of the post processing, the part is kept in a furnace at a certain temperature for a certain amount of time. Hence, the low melting point material burned away. The part at this stage is called as the brown part. In the second stage of the post processing, the brown part is further reheated while in direct contact with an infiltrate material. At this stage, the infiltrate material flow by the capillary action into the pores of the brown part to produce fully dense parts. Usually, if I take an example of the metal like steel, and we utilizes the powder particle, those are coated with some thermoplastic, and we produce a green part onto the powder bed. After taking out this part and keeping it into the furnace, we increase the temperature typically around up to 200 degree to 400 degree centigrade, so that the binders just burn away from the part and leaves the pores behind. We further increase the temperature of on this stage, and the brown parts are produced. Later on, these parts are kept in direct contact with the infiltrate material, and due to the capillary action, these infiltrate material, like in this example we can assume to be the copper, they just rise into the, due to the capillary effect, into the pores and fill all the pores and produce the 100% fully dense parts. Of course, in this technique, obtaining a monolithic part may be a challenging task. So, one very important thing we can note in the case of indirect route of SLS, no compaction pressure is applied. As a result, while the green parts are of lower density, they are nearly isotropic. You go in any direction, the property remains same. That is why they are free from any internal stresses as well. While the latter two features are desirable, having a part that is isotropic and free from any internal stresses is definitely desirable, but the former two, that is the green part with lower density, are not really desirable and may lead to some problems because the strength of the part may be less. However, this less strength will be everywhere same because the part is isotropic, but it is not going to give you very good strength because of the lower density. So, for instance, if the part density is too low, it can even distort during the post processing in the furnace or get damaged during cleaning or handling the part while taking it from one place to another place. Thus, it is desirable to aim at a green density that is at least 50% of the theoretical value of the final part and a strength value which is around larger than 1.7 megapascal, so that we can efficiently handle it. The key advantage of SLS is capability of yielding functional part in essentially final materials. If you compare the parts produced by this process, they will be definitely having considerably high strength as compared to the parts produced by SLA, because here you are making at least the parts of metals. Also, no support mechanism will be required. So, this is an important thing. Because here we are not melting the metal particles, right, and only melting the polymer which is around it, which is creating a matrix and producing a green part. Later on, as therefore the loose powder which is available under the powder particles getting melted in any overhanging feature, for example, they will be supported with the loose powder. Hence, no separate support mechanism is required. Later on, this loose powder can be removed easily. Further, the process is simple. Example, there are no milling or masking steps required. Uncured material is easily removed after building just by brush or blowing it off by compressed air. This video is a typical example of utilizing the laser beam based powder bed additive manufacturing process where the ceramic particles are coated by the polymers. You can see here the polymers which are coating around the ceramic particles are getting melted and they are making a bond with the adjacent powder particle which is similarly coated with the polymers. Here one can see there is a laser beam writing on the layers and selectively it is hatching the region or moving into the region where the particles needs to be joined. The process will repeat itself, spread another layer and hatch the cross section which we obtained by the slicing operation which we learned in our module 2. So in a similar fashion, the process repeat itself and build the part. Now, as a result, the part you will produce here will be a direct sand mold which can be utilized for casting. And of course, these particles of the sand are held together by a polymer. So of course, a post processing will be definitely required. The overhanging regions which are supported by the loose powder will be easily available here and the loose sand can be removed. Later on, the mold which is available inside by simply removing these loose powders either by the brush or a compressed air. So as you can see here, the overhangs doesn't really having any support structure which need to be removed by external process. It is very easy now to remove the support because the support is nothing but the loose powder. Once these molds are ready, as I said, they should have sufficient strength that one can easily handle them and take it to another stations. Then in the next stage, the entire mold is kept into the furnace where the binders are going to be removed. After this stage, the parts which we will be having here will be having very low strength. Subsequently, at the same time, the infiltrated material rises under the capillary effect and fill these pores. As a result, we used to have a very strong part produced by this method. And it can be noticed that it is nothing but a direct sand mold. Now one can directly pour the material into it and get the part created. So far we have discussed about the powder. Those are coated with thermoplastic materials, but it is also possible to have a mixture like you are seeing here in this diagram. So here there are powder particles which are of maybe ceramic or maybe it could be of metal, and there is a binder which is of low melting point temperature. Example here, it is an epoxy resin. After the laser beam will move over it, this low melting point binders will get melted and form the matrix. As you are seeing here, the sintered part will look something like this in this case, and of course it is in the green state. Later on you have to eliminate these binders and the part should go through an infiltration process. So why at all it was required? Because the coated particles are usually expensive and it is also sometimes very difficult to maintain the uniform layer thickness around these ceramic or metal particles. However, in the case of the mixed particles, it is also possible that the powder particles, those are mixed, got segregated while a recoating blade moves over the blade. This phenomena has to be taken care, of course. So in summary, we can say that if we are going through the indirect route of selective laser sintering, then either the coated particle or the mixed particles are possible materials to be used in this case. Next, the powder material for direct route of SLS. If you are going to process the polymers, there won't be any issue because polymers are already the low melting point particles and they can easily fuse and make the or get sintered with the adjacent particles. So if the polymers are processed directly without using any binder or coating or mixing. However, in the earlier stage, to produce the part by direct route, the mixed or pre-alloyed metal particles are used. It was difficult in the beginning, like to use a pure metal to build the part, and that was very difficult with the high melting point temperature particles. This is mainly because of the boiling effect, which usually occur due to the unavailability of the high power diode or the fiber lasers. So what happened when the laser power is low? Due to low laser power, the sintering necks are formed with a limited liquid amount region. And what is that region? It is nothing but the region where our focused beam spot is there. So assume that at an instant, this is the laser beam spot on the bed. Now only in this region, the liquid material will be available. Similarly, if we consider another spot, after some time, in this region only the liquid material will be available. So if we look at the powder particles, those are joining these two consecutive spots, and just look at here in this diagram. Conventionally, it should happen that there must be some liquid region available here, and that will be called as the sufficient liquid formation, and that will give us a continuous sintering track. Hence, the powder particle melted at this particular instant will be forming a bridge between the particles getting melted at next instant. Hence, you will get a uniform single track deposited on the substrate. But if the laser power is low, not only the laser power is low, but it may also be possible the power is sufficient but material is not absorbing the enough power from the laser. Also, it has been found that the metals are more compatible with the low wavelength laser such as the diode or fiber laser, where the wavelength is around 1 micron. But in earlier stage, we used to have the CO2 laser only in the high power range, and that was of around 10 microns in the wavelength. Therefore, those lasers were not really very much compatible with the metals to get processed. Therefore, the region where the liquid region is generated was very much restricted. As the unavailability of the liquid material between the two consecutive states at time t1 or maybe time t2, the bridge formation will not happen between these two spots. As a result, we will deposit nothing but the balls of liquid material at different locations when the laser beam is moving along a path. No continuous track was obtained. So this used to be the major hurdle in the earlier stage. So the molten material in the focus spot area of each point tends to aggregate into a single coalescing sphere whose diameter is approximately the diameter of the laser beam. At this stage, it was realized by some researchers that this effect of balling can be easily eliminated if we use two-phase powder particles, such as either the mixed powder particles or pre-alloyed metal particles. So in the earlier stage, the mixed powder and the pre-alloyed powder particles enables the direct SLS. So with the utilization of like two materials, either by the mixing of the two material, one may be of higher melting temperature and another of the low melting point temperature together, and then sinter by utilizing the laser directly onto the bed itself. No further post processing may be required. In such cases, 100% dense part were usually produced on the bed. This was the scenario in the early 2000. Then after that, later on, of course, the laser powder were available and the process was available with many researchers. They came up with many solutions and developed the window where this balling effect could be eliminated, and even directly the metal was used not only for sintering but melting. But at this stage, the direct SLS was produced only with the mixed powder or pre-alloyed powder. The first direct metal laser sintering DMLS machine was developed in 1995 by EOS of Germany. EOS INT M250 RP was a popular EOS machine that uses 200 watt infrared laser with a spot size of around 300 microns. The system uses a pre-alloyed powder particle that yields a laser cure width of about 600 micron at a scan speed of 3 meter per second with a standardized layer thickness of 50 micron. As it is mentioned here, you can see the pre-alloyed powder. Now, creating that pre-alloyed powder itself was a difficult task for anybody. Therefore, whenever you buy a machine at this stage of the time from a manufacturer, then of course you have to buy the powder also or the raw material also from them, because any material cannot work. I have already mentioned the reason. So, only the powder particle should be either the mixed composition or be pre-alloyed, and those were usually the propriety in the beginning. Also, the mixed powder technology is found to be applicable in the direct SLS of several mixture powders. The material to be sintered comprises of a structure powder, which is nothing but a high melting point powder, and a binder powder, which is nothing but a low melting point powder particles. This mixture of structure powder and the binder powder enables or promotes the liquid phase sintering at this stage. Sometimes in the mixture we usually provide a fluxing or wetting agent also that accelerates the wetting characteristics while the liquid phase sintering happen on the machine. So for example, while sintering nickel and tin, a mixture of nickel particles and tin particles, usually tin melts at a temperature of 1455 degrees centigrade, where the nickel melts at 1455 degrees centigrade, whereas the tin melts at 232 degrees centigrade, and the resulting compound can be composed of Ni2SN, Ni3SN2 or and Ni2SN4. It of course depend on that how many particles are available surrounding the nickel of SN. Those are getting melted while the laser beam scans over it. So laser beam usually melt this SN first, and the SN, the molten SN and the molten tin usually flows into the porosities available between the nickel particles. As now the SN is available in the completely liquid form, its flowability is of course good, and the wetting of these nickel particles is slightly higher. As a result, the two adjacent nickel particles will be appropriately connected by the liquid form of the tin. Of course, if the temperature will raise further, the compound will be formed like of Ni2SN, Ni3SN and Ni3SN2 and or Ni2SN4. So this is typically an example for liquid phase sintering. Of course, the nature of the liquid phase sintering will be clearly depend on the characteristic of the powder you are blending together as well as the sintering process which is happening on the powder bed. So these two processes were the most important and the governing process for direct SLS in the early stage. First, the pre-alloyed powders, and second, the mixed powders. And later on in the recent years, the idea of full melting metal powder is explored. It is supported by the continuously improving process parameters, smaller layer thickness, smaller spot size, high power lasers and all, resulting in mechanical properties being much better than those of earlier time selective laser sintering part and comparable with bulk metal properties. This this research towards the layer thickness, inert environment of the chamber, small diameter of the laser spot, small size of the powder particles, high power laser, they all enable together the process called as selective laser melting. So from now onwards, sintering is usually obsolete for the metal particles, and most of the laser beam based powder bed additive manufacturing are nowadays governed by the selective laser melting, where the 100% dense objects are produced in the bed itself, and usually no post processing is performed to increase its density. Of course, few other post processing are performed, but not for increasing the density of the parts produced. So now let us discuss about the next subsystem, which is the scanning system. There are three possible scanning systems available in the laser beam based powder bed additive manufacturing machines. First is the galvanometer, the second is the flying optics, and the third is the mask based system. Of course, the last option, which is the mask based option, is not really very popular, but the first two are quite popular. Among that, even the first one, which is the galvanometric system for scanning or moving the laser beam on the laser bed, is quite popular. We have already seen this method of galvanometer in our module number 3, where we discussed about moving the laser beam, UV laser beam, on the liquid tank of the wet photopolymer. Similar galvanometer is used here. The only concern here is the galvanometer should be having some additional cooling mechanisms as well, because here we usually deal with the high power laser as compared to the laser used in the case of SLA. Of course, we also seen that when a laser beam strikes on a galvanometer, it projects it onto the powder bed. As the position of the galvanometer changes, the striking beam can move here and there on the bed. We have seen as the laser beam is projected away from its center line, then the shape of the spot may not remain circular, which we are obtaining here, but it may distort and change it to the elliptical shape. Also, as this length F1 is different from this length F2, its diameter may also change. The spot may become larger because the focal point is same. Therefore, usually the beam correction method has to be used before projecting the beam onto the bed itself. Typically, in the case of SLA, when galvanometer is used, an F theta lens was used. We have already seen that. Similarly, here also in the laser beam based powder bed additive manufacturing, F theta lenses are preferred. We have already seen the purpose of using the F theta lens and their working principle as well. So, as a result, if a F theta lens is used, it will direct the laser beam vertically downward everywhere on the bed, as well as the correction in the shape of the beam will occur. This is called as the passive optics for beam correction. While there is another popular method nowadays coming up in the laser beam based powder bed additive manufacturing, and that is called as the active optics. This is because the F theta lenses, those are used in the passive optics, become very inefficient when we deal with the large working areas, because in that case these F theta lenses become very big, costly and unpractical as well. And that is why with these systems usually the size of the bed is limited to a particular size. While the another alternative came into the picture, which is nothing but a active system. This alternative 3-axis scanning system with active optics are gaining acceptance in the laser beam based powder bed additive manufacturing. In a 3-axis scanning system, a dynamic focusing module is located just before the laser beam enters to the galvanometric system. In this DFM, in this dynamic focusing module, a flat field is achieved and a third axis, Z axis of the motion is introduced in the form of linear lens translator. So, the DFM provides a motorized focus optics. So, there is a motor here. So, this motorized focus optics manages not only the focal Z height, but also the flat field correction, working distance and spot size as well. So, for example, there are few lenses inside this DFM. I am just trying to explain this briefly. If I change the distance between two lenses, then of course the focal point of the laser beam will change. So, if I am projecting it away at a particular location, then of course I will change the focal length dynamically here into the dynamic focusing module. So, this active change in the laser beam spot size focal length which is projecting on the bed gives us freedom to increase the size of the bed as well. The next option is the flying optics. Like we discussed in our module 3 for SLA, here also in the case of flying optics, the entire optics which is projecting the laser beam moves on a XY table. And as the optics moves on the XY table, now it is always perpendicular to the bed on which the laser beam is striking. As a result, there won't be any issues related to the focal length change as well as any issues related to the distortion on the cross section of the laser beam projected on the bed. However, as the entire optics is now moving, we have to limit the speed or the scanning speed of the laser beam for creating the part. That will definitely affect the production time and that will increase in such cases. The another one is the mask based system, though such systems are not much explored in the case of the high power laser used in the laser beam based powder bed additive manufacturing system, but few researchers have explored this technique where multiple lamps are used and instead of a laser beam, the projected floodlight falls onto the mask. We know that this mask will stop the light wherever it is not required and it will allow only the light to pass through the region where the material has to be melted or sintered on the powder bed. So, these are the possible scanning systems for laser beam based powder bed additive manufacturing. Next is the powder delivery systems. There are popularly two types of feeding system. One is called as the top feeding, another is called as the bottom feeding. In the case of top feeding system, which is shown here, the hoppers are available on the top side. The powder is delivered till the recoating blade or till the recoating system under the gravity. This is also called as the top feeding system. This is called as top feeding system because the material is feeding from the top side. Another one is the bottom feeding system. In the case of bottom feeding system, the material is fed from the bottom side. As you are seeing here, there is a reservoir here, there is a reservoir here which is having a lot of powder available, and the right side is the build platform. Now, the material will be delivered to the recoater not from the top, it will be delivered to the recoater from the bottom. So, as the material is getting available to the recoater from the bottom side, it is called as the bottom feeding powder delivery system. Such systems are still much popular in the case of the laser beam based powder bed additive manufacturing as compared to the top feeding systems. Few commercial systems like SLM, they use the top feeding system, while the top feeding system is also popular in the machine of RCAM, where instead of laser, electron beam is used as an energy source. Other than that, most of the commercially available laser beam based powder bed additive manufacturing systems utilizes the bottom feeding of the powder or the bottom feeding powder delivery system to deliver the powder towards the recoating system. We will discuss these topics in the upcoming lecture. Thank you very much.